We are now looking at drawing layout. Now drawing layout, as you might have seen from the last class, it takes some amount of time. So to reduce the time, we can draw what is called a stick diagram. Stick diagram. So all the information that we put in the layout, you can also include in what is called a stick diagram. For example, let's take example 1, and this is pretty fast compared to drawing the layout, the full layout. So Nand 2, we will take that example again. Now Nand 2 circuit, if I just repeat, all of these are with respect to Cmos. So this is VDD, and then we have 2 Nmos in series, and then we say A, then B, A, then B. So if this is the gate, and if you, so gate sizing, I hope you remember, this is 2, 2, 2, 2. Okay, so now let's draw the layout of, the stick diagram, not the layout, stick diagram of Nand 2. So first thing is draw power rail with just a line, blue color line. Okay, so this is, one is basically VDD and the other is basically ground. Okay, so we don't show that width information, only just a line we use. Okay, so it looks like a stick. Then we will use say orange or yellow color to draw the P diffusion. So we will draw another line for P diffusion, and then for N diffusion we have to use green line. Let's draw it a bit more straight, and then what is left is polysilicon. So for that we use the red color. Okay, so I'm drawing polysilicon. Okay, now we have created transistor. Wherever poly crosses with the diffusion region, we have transistors. So 4 transistors are created, 2 Pmos and 2 Nmos. Okay, again we don't show explicitly here N-well, just like in the case of layout, we did not show that. Now all that is left is now making connection. So before making connection, we need to identify the source and drain of the different transistors. So if you look at here, this is source and these are drain. So drain, source, drain, source. So this is the way it is to be connected. So we will say this is our drain, and automatically this will become source, and source are connected, and then this will be our drain. Okay, so then similarly we will say this is drain, and then this will be source, and so this will be drain and this will be source. So in order to make connection, we use the black color. So we will draw black line between the power or the ground and connect to the diffusion region. So for example, make the source connecting to the ground. Okay, so let's say this is transistor B. Okay, so let's denote that this is B and this is A. Okay, so to make the connections, what we do, source of B, transistor B, Nmos is connected to ground. So we draw a black line and to this cross mark to show that these are contacts. This is how we draw the stick diagram. So it's pretty fast, you can quickly draw, and this is a shared diffusion region by the 2 transistors, and then you have another metal lines connecting like this. Okay, so this is transistor A and its drain and its source. Now we need to connect it to the power supply. Okay, now what is left? The drain of the two Pmos should be connected together, so that we can do by taking a connection like this. So there we don't need to show because it is the same color. We don't need to show the contact there. In fact, we don't need to show the contact here also, because that's just a metal line. So both of these are metal line. So you can just leave like this. Okay. Similarly here also. But wherever there is a diffusion or a polysilicon, we need to show the contact. Okay. So that's the stick diagram of Nand. So let's take another example. Example 2. So let's say NOR 3. So first draw the circuit diagram of NOR 3. So in NOR 3, all the Nmoses are in parallel. So A, B, C. And then you have a series connection of Pmoses. A, B, C, and finally VDD. Now what will be the sizing? So if you look at the sizing, this will be 1, 1, 1, and what will be the sizing here? It will be 6, 6, 6. Okay. I'm not going into the details because we have discussed the details how to find the sizing of transistors earlier, and the sizing will decide your resistance and capacitance of individual. Okay, so in order to find out the sizing, all that we look at is the resistance, okay, for charging and discharging. It should become equal to R. So we have to adjust the size of the transistor such that in the worst case we will have a charging and discharging resistance, path resistance should be equal to R. Okay, where R is the charging and discharging of a reference inverter resistance. So we have to compare it with the reference inverter and try to achieve the same. Okay, let's draw now the stick diagram. Again, first thing is draw the rail. This is the power supply rail. Okay, one is VDD, the other is ground. Okay, then we draw P diffusion. So that is with the yellow color, and then we draw N diffusion. It is with the green color, and then we have to draw on. So there are 3 inputs, 2, so 3 polysilicon. Now you have to be careful how we are going to name them, A, B, C, or B. You can name them as ABC or CAB or BAC. Okay, so that will decide the way it will. You have to, while naming it, you have to consider both sides as the circuit, CMOS circuit become more and more complicated, this become more tedious. Okay, so as you can see that I am putting A on the PMOS transistor with input A at the bottom where I am going to take the output. So I will name this as A, and then this as B, and this as C. Okay, so denoting, so this is drain, then source, drain, and then source, drain, source. Okay, so now we have to make connections. First of all, let me make the connection between the Pmos and Nmos here. So I take the black and then I connect. Okay, so this point is my output. Now, so this DD got connected. Now if I look at the Pmos side, so this is drain, then this becomes source, so drain, source, and then drain, source. Okay, so that is this source of the C input Pmos is connected to VDD, and then these are shared diffusion region, so already they are connected, we don't need to make any contact there. Now coming to the Nmos side, what we have to do, so let's mark the drain and source. So this is drain, automatically this becomes source, then this has to be source and this has to be drain, because all the sources are connected and all the drains have to be connected. So whatever is sharing, they should have the same drain or source, and this should be source. Okay, so now this source has to be grounded. Source has to be grounded. Now is it complete? No, it is not complete, because there is one more connection that is left, that is basically this drain has to be connected to the, so drain of C and B are connected, but it is not connected with A, so we need to make that connection. Okay, so this is how, here one shared diffusion region is there, but here there is a shared diffusion with the contact. So whenever there is a contact, the spacing will be larger, and accordingly the capacitance will go up. Okay, so capacitance of different nodes will depend upon the layout, or so stick diagram is basically a quick way of drawing the layout. So all information in the layout is here. Only thing is that we are not specifying anything about the sizing. I mean sizing means length, width, perimeter, area of the diffusion region. These are not specified here, so those details are missing, but the way in which we are going to put it, so that is mentioned here. Okay, but sizing you can mention like this, so by writing the numbers in the circuit diagram. Okay, so now let's take a more complicated example. So now you will see that things will not be that direct. So example 3, let's take A plus, let's say y is equal to A plus BC plus DE whole bar. So this is the function that is given to us. So earlier everything was standard function. Now let's see what happens. So first let us create the CMOS circuit, which is not difficult. So first let us do that. So you have, if you look at the Nmos side, you have A. So that's A, and then you have BC. So B, C, and then you have DE. Okay, so this is grounded, this is grounded, this is grounded. All of this are in parallel. Now how do you draw the Pmos side? Just basically take the dual of this, okay, and put P transistors there. So that means wherever it was parallel, it should become series. So I will put, there are multiple ways I can put. So I can say that this is A, and then I'll put 2. So this will be Pmos. I have to put the bubble B, then C, then I have another. So this is D. Okay, so this is VDD. I completed my circuit. Now the issue is that in the layout or stick diagram, how will you order the polysilicon? Okay, so we have one vertical red line corresponding to each gate, which is common connection for both Pmos and Nmos. So this becomes a problem as the circuit become more and more complicated. So let us try. If we don't succeed, we will formulate some strategies. Okay, so let's just try as before. So we will start with the power rail, and so this is, so one is VDD, another is ground. Okay, so then I have yellow for P diffusion, green for N diffusion. Then I have to draw vertical lines. 1, 2, 3, 4. Need one more. So okay. Maybe I should extend a little more. Okay, so this is now you need to know how to connect. It looks like, let's start with an A here. Okay, A, and then let's see what happens. B, C, D, E. It may not work. I'm not sure about it. If you are lucky, it may work also. But let's see what happens. So let's put in the information about the so this is going to be drain. No. So this is source and this is drain. This is drain, 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 then source, source, drain, source, drain, source, drain, source. So for Pmos, we have source, source, drain, drain, source, source, drain, drain. Okay, so let's try to connect them. but as I said, we may not succeed now, but let's try. So this has to be drain. So if it is drain, this has to be source. And then for B, here is B. Okay, so for B, so problem happened here itself. So the source of A is connected to ground, but source of B has to be connected to the drain of C. Okay, so we can't now draw it. Okay, so source of A has to be connected to ground. So if I connect this to the ground, then if you say that this is B, that will be a problem, because B don't have any ground connection. B has either connecting to the drain of A, and source should be connected to the drain of C. So the way in which we have ordered this gate terminal will not be proper. Okay, so this is the problem that we will run into once the circuit become complicated enough. Okay, so then we have to delete everything and then reorder them. So how to reorder them, that we need to find out. So there is an algorithm called Euler's shortest path algorithm. Euler's, probably you might have heard from some contexts, maybe in mathematics. Transportation problem. It's a transportation problem basically. So we will draw the graph of this circuit. Okay, so how to draw the graph? So basically each transistor will become like a branch of the graph, and then there are nodes in the circuit which will become the nodes of the graph. Okay, so for example, if you draw this, you can draw like this. So then there is a node here. Okay, and then you have a single. So this is the different nodes. These are different nodes, and you can name them. This is A. The branches you can give the names A, B, D. What did I say? This should be E. So E, and this is C. So this is the Pmos circuit graph, and similarly I have to draw the graph for this. So this is A, and then we have one node here. The node I am just denoting with these bubbles. So this is going to be B and C, and then I have one more. Okay, so this is going to be D and E. Now we need to adopt the algorithm called shortest path algorithm, which has some restrictions. The restriction is the following: every branch should be traversed but only once, and we need to cover all the branches. Okay, so all the branches has to be traversed, but going through it only once. So we can put an arrow. So I can just show you one way we can do it. So for example, if you start from here, then you go here, then go here. Okay, so starting here, going here, and coming back. So I have traversed all the path, and only one time I have traversed. Now similar order if I can find for the bottom diagram also, then we can keep that order for the polysilicon lines. So let's see whether we can make that order possible or not. So I go through A first, then I go through B, but then I have to go through C. So you see that already contradiction. Okay, earlier I have went through, so that will not work. Now if I just continue this, I can go through E and then D like this. So the order in which, so let me write the order. The top one is like A, then B, then D, then E, then C. The bottom one is A, then B, then C, then E, and then E. So all of this satisfy our requirement, but they are not same. So we need to change one of them so that both will become same. So let us try to change the top one. Can we make the top one similar to that of the bottom one? So that means we go to A, then we go to B, then we go to C. No, that will not work. So I cannot make the bottom one looking like the top one, nor can I make the top one look like the bottom one. So I need to try a different scenario. So I'm just deleting it or going back and doing it. Okay, so let us start somewhere else. Now this time I'm going to start from here. C, E, D, B, A. So that means C, E, D, B, A. Can I do that? Now if I start with C, then I'll go to B, or I can do this another way. I can do it. So I will start at this node C, then E, and then D, but then I cannot go to B, so that is also not possible. Okay, so that won't work. So I have to again try something different. Okay, so okay, let me just try this. I will start with E. That will work either. Okay, I'll start with A, then I'll go through B, sorry, I will go through C. That will also not work. So you see, become tedious. Okay, so let me start with where can I start? One thing is sure, I have to either start with A, E, D, then B, C. difficult. Anybody, if you get an idea, let me know. Both graphs I can order it in the same manner. Okay. Okay. Looks like there is no solution to this, or is it because I did not look enough closely? So I am not able to find a solution for this. So what I will do is that I will exchange this and try. Exchange this and try. So this I will make it as DE, and this I will make it as BC. I just exchange it. BC are parallel, D are in parallel. So okay. So in that case, it will become D E B C. Now let's try again. So I go with A and then D, no. It's the same story. Okay, so then this doesn't have much difference. Okay, then I will do one more modification. I will put the A in the middle, and I'll put the A in the middle and then DE. So this should work. That will give you more option for A. Otherwise A has to be either at the starting or ending. So I have to change the circuit. So I will have one Pmos, which is A, and then two Pmos. So parallel with the another. Okay, so this is our DE. Okay, the circuit will be okay. It will implement the logic. So in multiple ways you can draw the circuit, but some of the way it will be easier for us to find the Euler's path. Okay, now let's try again. This time I hope I will succeed. So I can start with, say, this point. I can go D and then E, then A. Yes, this time it will succeed. B and C. So I can do the same thing here. D, then E, then I go through A, and then B, and then C. Okay. So the order in which I have achieved is I started with D, and then I went to E, then A, then B, C. So same thing here also. D, E, A, B, C. Now if I start with A also I can no, I cannot do it. If I start with A I cannot do it. Maybe I can start with B also. Another option is I can start with B. So B, C, A, D, E. Let's see. B, C, A, D, E. Okay, so this is also another option. B, C, A, D, E. So if you keep that A in between, we can succeed. Okay. So one of this order we can choose. Okay, so let us choose maybe the first one itself we will choose. So I will put D, E, A, B, C. So this is the way I am going to put it. Now we have to connect. Okay, so yeah, this is D. So D, Nmos D is here. So that should be connected to. So the source of the D transistor is connected to the drain of E transistor. Okay, so that is here. So that means this should be drain of E transistor, and therefore this will become source of the E transistor, and then source of the E transistor shares with the source of A transistor, and so this will be the drain of A transistor. So drain of A transistor is shared with the drain of B transistor, and this is the source of B transistor. Source of B transistor is sharing with the drain of C transistor, and this will be the source of C transistor. Okay, so similarly we have to look for the P side. So we are saying this is D. Now if you look at D, this will be the drain. Okay, so this is the drain, source, drain, source, drain, source. So D is here. So this is the drain, and so this should be source, and source is shared with the E. So this is the source of E, and this will be the drain of E, source of source of both D and E are connected, and the drain of E. Achha, there's some problem. D E A P C. So this is E. Source of E has to be connected to yeah, so sorry, there is an issue. D E A B C. So source of drain, source of drain okay, so let me just change this. So what is shared is the drain. E and E of E and D sources are shared. This is source. No. So let's make it drain. So let's take this as source and this as okay. So this is the source of drain of E, and then this will be the source of E. Okay, source of E is shared with the drain of A, and then this becomes the source. Now that is shared with the either B drain, so this will be source, and this will be source, and this will be drain. Okay, so we have succeeded. So now let's make the ground connection. So C source is grounded. C source is grounded. Then E source should be grounded. So this is E source and A source, both should be grounded. Okay. Then drain of all this, drain of A, B and D should be connected. So this line you can draw with blue also, this line, because that is metal. Okay, all the drain. So drain of D, drain of B, drain of B and drain of A, all are connected, and source of E, A and C, source of E, A and C, all are connected. So bottom is done. Now we have to look at the top. So C transistors source should be connected to VDD, and B transistor source should also be connected to VDD. Then what else should be connected to VDD? There is nothing else to be connected to VDD. Then drain of C and B should be connected. Drain of they should be connected, and it is the source of A. It is the source of A. Okay, that is also connected. Then what else? And the drain of A. that is this point. Drain of A should be connected to source of E and D. Source of E and D. So that means like this. Okay. Okay. So let me put that. Let me put it like this. Okay. And then finally, the drain of E and D. Sorry, E and D. E and D. So that is this. Should be connected to. So this is the stick diagram for this given logic. So as you can see that it's not that easy to draw the stick diagram or layout or finding out the appropriate way of connection. So you need to use this algorithm is called Euler's shortest path algorithm. Okay, so that's what we are making use. Otherwise it becomes with the help of that we are able to find out the connection. Okay, so do many problems similar to this that will help you to understand. Okay, now I move on to another topic. So delay, or let's do something else. Driving capability of the Cmos logic gate. Okay, so whenever we talk about driving capability, so there will be a load will be usually capacitance load. So if there is a gate, say Nand 2, NOR 2, NOR 3, etc., and the output will be connected to some load, and that load will be usually capacitor, load capacitor. Okay. So this will be apart from the parasitic capacitance, there will be a load capacitance. Now depending upon that load capacitance, sometimes the load may be very large compared to the parasitic capacitance. Okay. So in such cases, for example, you have a NAND gate like this, say 2 input NAND gate, and suppose it is driving another gate, say an inverter, which is a huge inverter. Huge inverter means the sizing of this inverter is very large, say something like comparing to the reference inverter, it may be something like 32 times. The size is 32 times. So when I say 32 times, what I mean is, so this means I have an inverter whose area and length are sized. So usually what we have for reference inverter, we have 1 and 2. So this will be, instead of 1 it will be 32, and this will be 64. Okay, this kind of huge inverter. Now if this is going to be the size of the inverter compared to the reference inverter, the capacitance will scale up and the resistance will downscale. Now the delay of this inverter, due to the parasitic capacitance and parasitic resistance, will be the same. Okay, so because if you draw the equivalent circuit of this, so this I can draw the equivalent circuit. So if I draw the equivalent circuit of this, I will have a resistance. So this will be R divided by 32, and this will be charging a capacitor. So what will be, so this is the charging. Okay, so we have here VDD. The capacitance will get charged like this, and the time constant here. So this capacitance value is how much? It will be 64 plus 32, which is 8, so 96. So the capacitance will be 96 C. So the time constant, if you calculate, will be given by RC. So that means R by 32 into 96 C. So what is that? Amounts to, it will amount to 96 divided by 32. That is 3 RC. Now, if you compare it with a reference inverter, we had the same, right? We had a 3C and R. For reference inverter, if you compare, it was basically, so this is my reference inverter. So this was R and this was 3C. So you can see that the delay has not changed due to the parasitic effect. The reference inverter delay is exactly the same as that of the scaled inverter. Okay, so we have scaled in order to basically we change the size of this, or scale the size in order to increase the current capacity, because it may be feeding, the fan out of this inverter may be very large. Okay, it has to supply to I have to put a bubble here. Okay. So if the fan out is very large, then it has to give current to various places, various inputs. So that is why we scale. Now suppose this is a scenario, I have a big inverter at the output. So its input capacitance is how much? So its input capacitance, if you look at the input capacitance, which will be my load. Now what is going to be the input capacitance? Basically the sum of the Nmos and the Pmos capacitance. So that is basically Nmos has 32C and Pmos has 64, so it will be 96C. And suppose this is a unit Nand gate. Unit Nand gate means the Nand gate which has same resistance when it is compared with the reference inverter, charging and discharging resistance. So we have basically the circuit look like this. So A, B, so this is VDD, and then this is my NAND gate, A, B. Okay, and the sizing was the what? So this is 2, 2, 2, 2. So if I look at the parasitic capacitance, so this is the load is 96C, and the parasitic capacitance of this inverter, unit inverter, is how much? So there is 6C. The capacitance is going to be 6C. So the parasitic capacitance here is 6C. Okay. So in such cases, you see that parasitic capacitance is much lesser compared to the load capacitance. So in this connection, so the output of this NAND gate, the delay of this NAND gate, is going to be decided mainly by the load capacitance, because it is 96C. This is all, parasitic is only 6C, so that is very negligible. So it's almost like less than 10%, very negligible. So the delay is going to be decided by the load capacitance rather than the parasitic capacitance. So this is one extreme case. Okay, so it depends upon what stage is going to follow the current stage. So what is going to be the delay? We are looking at the delay of the NAND gate, so that will depend upon what is the stage that follows. So here we have considered a stage where it is giving, the NAND gate is feeding input to a big inverter which has 32 times the size of a standard inverter. Okay. So if I write the delay expression, so for example, I consider the charging. The worst case is I have R, then so this will be 6C plus 96C. Like this. So what is going to be the delay? So the delay of this is this NAND gate is going to be R into 6C plus 96C. Okay, so this is the delay delay offered by this or delay presented by this stage, the NAND gate stage. Okay, it's the delay of the NAND gate, and that depends upon the resistance through which it charges the output capacitance. Output capacitance has two components. One is the parasitic capacitance. So this one is the parasitic, and this is the load. Okay, so load is huge compared to parasitic capacitance. So now, in order to reduce this delay, what we can do is increase the size of the NAND gate. So that is what we will see next, but now the time is up, so I will stop here. We will see that in the next class.